is really more apparent when we're looking at this kind of geometry, right? Now, first, let me show you this kind of profile in the real cat. This is the outer body, right? Of course, it's only half because it is because it is symmetric, and we see that the mandrel, which is there, right, is connected through some mandrel supports. This is the support, that is the support. Now, of course, the mandrel does not look as it is displayed here, because this looks like one big block, but that's never made that way, because they really have 3 plates here, and the mandrel really consists from plates. Each plate needs to be hauled through these mandrel supports to the outer body, and that's why we see on the outer body also the mandrel supports. The body and the mandrel, they create in between the flow domain. So, well, this is the flow domain we'll be looking at. We see here 2 polymers coming in, one from here, from the bottom, and one from the side. And of course, if you look at it and if you know that these polymers are different, then probably this is co-extrusion. Everybody would say we can't solve it. No, we can, right? And in fact, if you look at it, they only join right here. There is interface right there, and probably through here we have some crossflows. We don't have too many crossflows at this merge because this is very close to the exit and the polymer simply wants. We never meshed the whole full flow domain. We were doing the mesh like this. It was split into segments, you see, and only these particular segments were meshed. Why? Because there is a straight connection between these sections. So we don't need to mesh them, right? We need to mesh by automatic mesher only these narrow sections. And then at the end, when we do it, we just end up with the complete long elements here. And then we can bring them to our program. The advantage is that we save a lot of elements here, and we have a very good quality mesh with lots of elements across, and also these sections here are very straight. Now, how that was made this way. So you see, for example, on this particular section, we have, I think it's about six domains, and you see one is this one here. So those are independent meshes. You can see they're right made like this. And then I can look at the other one, and those were the parts meshed automatically, and these parts were simply extruded, right? So you see, these are the independent meshes. The program allows one very useful function. It allows to solve them together as one block. You can select this and start the solver, right? For all of them. If you do this, and if these meshes are conform at the interface, then the solution will behave exactly as it would be one flow domain. Well, of course, if you want to merge them, no problem. You can always copy for merge, and then once you copy for merge, you can paste from clipboard, and that will merge these 2 meshes into one. That's how this one was made. You see, we have here only 2 meshes, one and the other one. So I can, in fact, choose if I want to solve this big die as, consisting from 2 meshes, one for each polymer, right? And they are connected only in here, in this narrow section and that narrow section. And in fact, you would see some crossflows because they influence themselves. Or I can solve them like this with multiple grids, right? Now, what is the advantage? Well, of course, the advantage of solving together is that I can let's say put a path line and see the path line to go through. But when I was explaining the merging, I can very easily merge these 2 geometries. Okay, let me show you. Copy to clipboard, and I will make now a paste from clipboard. So that will create one extra copy of that mesh. Right, let me see which one it is. That's the one. And I need to identify that section here. which is probably, yeah, it's this one here. So I can just say copy for merge, and I can merge these two. I will rename it to merged. And I say paste from clipboard. And now he's trying to find out the intersection. And now he did merge them. So you see now I have an extra mesh here merged. Now this is one mesh. It's together. So now if I want, I can put here, let's say, velocity, magnitude, or any other variable, and it will work simply as one mesh. And at the same time, I can put a path line, and I would see a path line going from the beginning to the end because it is really a one mesh, right? So even though I've solved them independent, I can merge them after the solution. The solution is identical. Now, is there any meaning why I would like to keep them independent, right? Is there any advantage? Well, of course, there is an advantage because we can only decide to solve, let's say, one of them. I want to see, for example, flow on this particular section, right? I don't have to solve the whole geometry, right? It's enough for me to put here the entrance mass flow rate and to see how they flow. Why? Because if you look at the post-processing of the complete case, you see that these sections have basically no influence on that one. That one is very much self-defining the flow, and it will really dictate the flow. So if you do this alone, you will get a very good distribution exactly as we have it here. If I would show you now, see these geometries here were solved independent. So I can just hide the ones I don't want. Okay, that's the section we're looking at. And if you look at the exit, I'm sure you'll be getting the same results as here. Basically the same picture. Only probably the variable scale is different, so the colors look slightly different. But if I would use the same color scale, we would see exactly the same picture. Okay. Of course, we see some advantage when doing this two meshes only, right? And one of the advantages is that we can see the crossflows, so we can see really how these polymers interact, right? If I would use now global limits, you would see that these two pressure contours, they in fact match when you give them the same variable scale. And it also indicates that the polymer really has some small tendency to crossflow, right? This one is going there, but not too much. That is really not dominant. More or less, it is very negligible because this is effectively separating the flows quite well. Okay, we don't see any crossflows on this side. So solving the geometries together one for each for one polymer, or solving them as separate meshes solved together, or sometimes solving them one by one, is giving us flexibility which we need. And what more, I can use this also to optimize the shape, right? Very easily I can solve only this geometry and optimize how do I change the gaps to get the flow rate required. For example, this one I can also very easily optimize. If I see that I don't have enough mass over here, or if the mass distribution is not ideal, I can put here some kind of polylines, right? I can do it like this, and like this. I can assign inside, and I can go to angle and say, okay, change this angle, apply mapping, and now I see my geometry is being deformed. So that's another trick which we will learn later on, but I can now change that geometry and resolve. No problem. I just start a solution right now, and I can get what is the distribution at this particular shape. Okay, so having the geometries or having the big geometry, big complex project to be split into segments, into parts, gives us the ability to correct one of them very fast, and then maybe remesh the whole thing and see the final effect. Okay. So that is about multigrid. Of course, the multigrid has some an important consequences in the boundary conditions which were added, because we need boundary conditions which connect them together, and we also need boundary conditions which are, for example, the back pressure. Because what and why that? Because of course, if I analyze only this part here, right? If I want to see the effect of this part will give me some distribution. I'm having this as a section which is supposed to distribute the mass to a little bit here, a little bit there, and would like to see the distribution. But of course, that will behave differently if you have the upper sections or not. So you can't ignore the back pressure effect. So we have to see what is the boundary condition here, and we will see that this boundary condition is boundary condition, this one, number 2, 4.16 megapascal. That's because before doing this mesh, we've solved the sections above, and we know that the sections above for that particular mass flow rate will consume 4.16 megapascal. So we said, okay, the boundary conditions is a resistor. It's a resistor which says for 7 kilo per hour, I consume 4.16 megapascal for temperature 250. So that means that I can calculate the distributor with the correct back pressure. And that's very important to use so the segments can be done independent from the rest, but you have to apply special boundary conditions. I would kindly ask you to check that section which describes this particular profile in more detail, or to look in our boundary condition section to learn more about what boundary conditions we use and where they are necessary. Okay. Thank you very much. That's enough for the multigrid approach, and feel free to follow the next videos. Thank you very much. Bye-bye.